Welcome, my name is Matthew, and in this video we're going to talk about factoring trinomials using the AC method, factoring perfect square trinomials, and factoring using substitution. So if any of these three types of problems look like types of problems that you need to practice, stick around. I'm going to work out a couple of examples for you. We'll see if we should be able to do a couple examples of each. Let me first mention that, let me first correct a little error up here. I'm really calling this 4.6. Some of you care about that, some of you don't. And these trinomials originally, I suppose, came from multiplying two binomials together. For example, you've seen problems like x plus 3 times maybe x minus 5, and we FOIL. X times x makes x squared, x times negative 5 makes negative 5x, and the O for the inners gives us a positive 3x, and the L for the lasts gives us a negative 15. So that was the FOILing process. This was the F, this was the O, the I, the L. And then we combine like terms, CLT, and we get x squared minus 2x minus 15. Now when it comes time to factor an expression that looks like this, we'd like to reverse the FOILing process. And when the leading coefficient is a 1, like it is here, and it says 1x squared, usually what we do is we go directly to sort of a wireframe of what we know the answer is going to look like, and it leads with an x squared, so we jump in here and we put in an x and we put in an x, and then we maybe ask ourselves, well, what two numbers multiply to get negative 15? Could be 1 and a 15, or a 3 and a 5. Ooh, a 3 and a 5. For some reason, that resonates with us because 3 and a 5 are only 2 apart from each other. So maybe we drop in a 3 and a 5 and we think, well, is one of them a plus? Is one of them a minus? What's it supposed to be? And we know that the 3 times the 5 has to equal a negative number. It's got to be negative 15. And maybe you just try them. If this is a plus and this is a minus, does it work? Well, negative 3 minus 5 does equal negative 2, and we figure we've got the answer. And in fact, we do. And I know that because I created the thing. It was originally x plus 3 times x minus 5, and so it is again. That kind of a process works quite well, especially if, at least this part of the process, when you're doing the factoring and this is the final answer, you can use the process that we just went through, and that's quite nice when it leads with a positive 1 on the x squared, and when this number at the end, a negative 15, when there aren't too many different ways you can factor the 15, 1 and a 15, 3 and a 5, not too many options there. You'll notice that all the problems to the left, however, are different. And the thing that makes them the most different is none of them say 1x squared. They all have larger leading coefficients. So we're going to need a different approach. There are other guess and check methods that you could use in order to try to factor these expressions off to the left, but a guess and check method, sometimes you guess right on the first guess, and then the problem didn't take so long. But if you have to keep guessing and guessing and guessing until finally you hit the correct pair of numbers in order to make the factoring happen, it can take a long time. So there's this thing called the AC method, which is nice because it involves the same number of steps every time. So while it is a little bit time consuming, at least you know exactly how long it's going to take every time. So let me demonstrate the AC method for you. I'm just going to use this space a couple of times. So first I'm going to write out my original problem, 12x squared minus 17x minus 5. And I will remind you that this is in standard form, ax squared plus bx plus c. So my a value is a positive 12, B is a negative 17, and C is a negative 5. And you'll see immediately why this is called the AC method, because I'm going to take my A value and multiply it by my C value. So that's 12 times negative 5, which is equal to negative 60. That says 16. I said 60 and I wrote something else. All right, there we go, negative 60. So that's my AC number. Some people call it the grouping number, and you'll find out why in a moment. The next thing that I do is I take my negative 60. I don't know what is wrong with me. It's like 8 o'clock at night. That could be what's wrong. I take my negative 60, my AC number, and other people do this vertically. I do this horizontally. I make a list of what I call factor pairs, pairs of numbers that multiply to 60 or negative 60. So let's be thorough. 1 and 60, 2 and 30, 3 and 20. Does 4 divide into that? It sure does. That's 4 and 15. 5 divides into it. That's where we got the 60 in the first place, was 5 times 12. 6 goes in, definitely. 6 times 10. 7 does not go in. 8 doesn't go in. 9 doesn't go in. 10 goes in, but we'd have 10 and 6 again. But we've already got a 10 and 6 as a 6 and 10. So we're going to stop our list there. Now realize that 1 times 60 does not equal negative 60. It either has to be a positive 1 and a negative 60, or a negative 1 and a positive 60. It's not very often that you see a plus and minus sign, and then, well, those we've seen before. But here's a minus plus sign, and I'm using these two, plus minus, minus plus, to indicate that these two numbers need to have, need to have opposite signs. And then we're going to choose one of these pairs. And I'm going to choose the pair that add to my B value, negative 17. And in this case, 3 and 20 are 17 units apart. And if I sneak in here and I make the 20 negative and leave the 3 positive, when I add those together, they'll add to negative 17. So that's the pair that I'm going to choose. And you should be taking additional notes, on your paper in this space over here. So we've chosen the pair that adds to negative 17. And with that pair, we're going to do what I call splitting the middle term. The 12x squared is going to stay the same. The minus 5 is going to stay the same. But the middle term, the negative 17x, we're going to write that as minus 20x plus 3x minus 5. How did I know to write the minus 20 first and the plus 3 second? It doesn't matter which way you do it. This process will work either way. Sometimes it's more convenient maybe to write them one way versus the other, but this is actually good because we're going to run into something that you don't always run into. And I always try to show you some variety in these types of problems. So let's stick with this. And I'm actually going to put an equal sign in front of this because it does equal the original expression that we're working with. Now that we've split the middle term, I'm going to do a process called factoring by grouping. And in the video previous to this one, you can find some examples of factoring by grouping. I'm going to take the first 2 terms and call that a group, and the second 2 terms and call that a group. And then from the first term, I'm going to factor out the GCF, the greatest common factor. And in the previous video, you can see different, at least a couple of ways of sort of tearing this apart and, good practices for factoring out the GCF. But I can tell that 12 and 20 are both divisible by 4. And this one has a couple factors of x, and this has 1 factor of x. So they're each going to contribute 1 factor of x. So here's the 4 and the x. And 4x times 3x would equal 12x squared. And 4x times negative 5 would equal negative 20x. You could also think of it as though I'm reverse distributing or dividing out a 4x from both of these terms. And then I move into the second group and I ask myself again, what's the GCF? What could I divide both of those terms by? And you might be looking at them and saying nothing. But there's always something. There's always a plus or a minus 1 that could be factored out. And so I am going to factor out a positive 1. And I'm even going to write plus 1. And then, what's 3x divided by 1? 3x. And negative 5 divided by 1 is still negative 5. What I've created now is 2 terms. Previously I had 4 terms. Up here I've got 4 terms. Now here I've only got 2 terms. Here's the first term, and here's the second term. And those 2 terms both contain a common factor. Visually, you can see it. It's the stuff in parentheses. That's the GCF. So I'm going to factor out my GCF. So my first term contributed the 3x minus 5, so that's gone. And my second term contributed a 3x minus 5, so that's gone. And here it is. And what's left is a 4x and a plus 1. So my leftovers are 4x and a plus 1. And that's it. We just factored a trinomial into the product of 2 binomials using the AC method. This technique can be used for all of these problems over here on the left-hand side. And you'll start to notice whether or not it's even going to be possible to do this factoring process using the AC method. Once you do a handful of these, you'll start to become quickly considerably better at it. 8 times 1 is equal to 8. There's a 1 and an 8, or there's a 2 and a 4. You can imagine making that list over there, not over there, over there. There, now my hand's in focus, over there. You can imagine making this list for an 8, a 1 and an 8, or a 2 and a 4. Hey, a 2 and a 4, I can use those to make a 6, right? Where's another one that just jumps out at me? Look at this one. What's 6 times 6? 36. So 36 is going to be your AC number. What's the first pair of numbers that multiply to 36? How about 1 and 36? Can you use those to make a 37? Absolutely. So you'll be able to factor it probably using the AC method. Where's another one? Well, you get the picture. 15 and 4. Now let's talk about perfect square trinomials. What in the world is a perfect square trinomial? A perfect square trinomial consists of 2 things. And the first thing I always like to ask is this. Is the number 49 a perfect square? And hopefully you said yes. And then I'm going to ask you, how do you know? And maybe you say, well, because 49 is 7 times 7. Perfect. I'm going to reframe the answer. See if you agree with this. 49 is a perfect square because it's the result of squaring something. In this case, it's the result of squaring the number 7. So a perfect square is the result of squaring something. If this thing's a perfect square trinomial, then it's a perfect square, so it better be the result of squaring something. It's for sure a trinomial because it has 1, 2, 3 terms. If it's got 3 terms, that makes it a trinomial. Now, if it's a perfect square trinomial, then again, it must be the result of having squared something. And this one is. Look at this. If I take 5x plus 6 and I square it, then I get 5x plus 6 times 5x plus 6. And if I FOIL it, I get 25x squared plus, sorry, it's not 5x plus 6, it's 5x minus 6. Too fast. I went too fast. Make those minuses, minus, minus, minus. All right, so 5x times 5x is 25x squared. 5x times negative 6 makes negative 30x. You don't have to write this down if you don't want to. It's not a bad illustration, but you don't have to write it down. Negative 6 times 5x makes minus 30x. Negative 6 times negative 6 makes positive 36. And then so I just FOILed. And then if I combine like terms, the 25x squared is still there. Negative 30x minus another 30x makes negative 60x. And there's the positive 36, which is what this says. My point is that this is indeed a perfect square because it's the result of having squared something. And it's got 3 terms, so it's a perfect square trinomial. I thought the cat was going to break the door down. I don't know if you could hear her meowing in the background. She just had dinner, so she's kind of insane. Maybe she'll join us later. Okay, so I've just proven to you, or demonstrated to you, that this does indeed equal this. The question is, how in the world did I come up with this so fast? I'll show you a couple of tricks. The first one is, we're going to do a little Q&A here, so make sure you're sitting up straight. What's the square root of 25? You say 5. What's the square root of x squared? You say x. So what's the square root of 25x squared? How about 5x? And then I'm going to ask you, what's the square root of 36? You say 6, and I say you're correct. So far it's looking pretty good. But now, what's 5x times negative 6? And the answer is negative 30x. And what happens if you multiply that by 2 or add it to itself? Let's even just add it to itself. What's negative 30x plus negative 30x? Well, that's the same thing as negative 30x minus 30x, which is equal to negative 60x. So that's how I knew that number 9 was a perfect square trinomial before I even started. Because the square root of 25x squared times the square root of 36 added to itself, or doubled, was equal to negative 60x. If you didn't follow what I just said, rewind it and watch it again. Watch that little segment. It's only like 10 seconds long over and over again until you see what it is that I'm saying. Because that's the test that you should be able to do just visually looking at a trinomial like this to determine if it is indeed a perfect square trinomial. If you can do that quick little test to confirm that it's a perfect square trinomial, then you can pretty much just write down what the answer is. How do you think I got that so fast? I took the square root of 25x squared and got 5x. I took the square root of 36 and got 6. I took... I've got too many lines now. Then I took this minus sign that's here, and I dropped it in between them, and I put a square on it. But you don't want to do that and write that down as a final answer unless you're sure that the original thing is a perfect square trinomial. So that's why I did this times this, and then I doubled it. And since it did indeed give me the negative 60x, I knew that this was the right answer. Let's do it all again. Why does it keep taking me up there? I'm just trying to go backwards a little bit, and it's taking me up there. All right, let's erase this by manually. If I zoom out, will it erase faster? All right, so let's confirm that number 11 is a perfect square trinomial. Square root of 36x squared is 6x. The square root of 49 is 7. 2 times 6x times 7 equals 36, 42, 84 equals 84. See the 84? So for sure, this thing is a perfect square trinomial. How are you supposed to write that into your notes? This equals, do I have room over here? Oh, I do. Ugh. I don't like when I hit the back button and it erases too much stuff. There we go. Equals b. Really, my b value is a negative 84, but close enough. We'll make that adjustment when we actually design the binomial that we're going to be squaring to get this thing. Since 84 equals negative b, 36x squared minus 84x plus 49, the original expression, equals, there are three things that we're going to put into this set of parentheses. The first one is the 6x. The second thing we're going to put in, the third thing really, is the 7. And the middle thing that we're going to put in is this minus sign. And that's your final answer. Could you do the AC method in order to factor these things to the left? 9, 10, and 11? Absolutely. Do you want to do all of that work to get your final answer? Or would you rather take the square root of some stuff, multiply these things together, double it, confirm that it equals the b value, and then pretty much just write down your final answer? I'd rather do that. I encourage you to do the same. So that is factoring a perfect square trinomial. And then this last section is about factoring using substitution. You'll notice that these things look an awful lot like a regular quadratic. All I have to do is erase this m minus 2 in here, and erase this m minus 2 over here, and put in an x instead, and now it says 5x squared minus 14x minus 3. I know how to factor that. I'd factor that the same way I factored all of these problems up here, using the AC method. So let's do that, except I'm not going to use x. I think maybe let's use a different variable. Let's use u. That's pretty typical. I'm going to say let u equal m plus 2. That way we can rewrite the original expression as 5u squared minus 14u minus 3. Okay, now we need to factor this using the AC method. So the idea of replacing the m plus 2 with the letter u is called substitution. We will replace the u with an m plus 2 at the end of this process. This just makes the factoring process a little bit cleaner, easier to read maybe. So let's factor this using the AC method. Factor by the AC method, even though that's illegible, you can hear me, so you'll write it down so that it's legible in your notes. And we don't want that equal sign. We want to write down A times C is equal to 5 times -3, which is equal to -15. And then I'll take the -15. I'll make my list of factor pairs. 1 times 15, 3 times 5. One's positive, one's negative, plus or minus, minus plus. We need to choose the pair that adds to the b value, which was a -14. I think we should use the 1 and the 15. What do you think to get -14? So let's use these. And one of them is going to be positive, one of them is going to be negative. It's the 15 that's going to be negative. The 1 will be positive, so that they add together to equal -14. So then we will split the middle term. Which gives us equals 5u squared minus 15u plus 1u minus 3. Let's switch it up. If we had written it up that way, it still would have worked, but in the second group, we would have ended up factoring out a +1 again. And so since we already saw an example where you factor out a +1, I'm going to switch those two middle terms so that the factoring by grouping process looks a little bit different. So let's write this as +1u minus 14u. Is it 14? No, it's 15, sorry. Minus 3, there we go. Oh, this is going to be a really good example of a slight difference in the factoring by grouping process. Okay, so factor by grouping. Let's make our two groups. Here's one, and then be very careful. You want your second group to include the minus sign that's in front of that 15 there. Again, this minus sign wants to be in your second group. All right. Now we'll factor out the GCF from our first group. That is it's a u. That's it. And the leftovers are 5u plus 1. We can confirm that by distributing. U times 5u makes 5u squared. U times +1 makes +1u. And then we look at the second group. The GCF in the second group is unusually a negative number. It's a -3. Last time we did factoring by grouping, it was a +1 that came out. Now it's a -3. Reverse distribute it. 5u plus 1. -3 times 5u makes -15u. -3 times +1 makes -3. We're doing well. We're factoring correctly. Ugh, it's erasing too much again. Darn it. Get rid of that. Sorry that this circle is in here. Bad. All right. Now we're going to factor again, because what we have here is a term minus another term. The common factor in those two terms is, again, the stuff in parentheses, which is the 5u plus 1. The leftovers are the u minus 3. And the question is this our final answer? And it's not, because the original question was written in terms of m, not in terms of u. We said that u was equal to m plus 2. Now that we've factored this as far as we can, we're going to replace the u value with an m plus 2. So you can call that back substituting, reverse substituting. You could write a little note over here that says replace u with m plus 2. However you want to write it over here. I typically say back substitute or substitute back. But you write it out in your little annotations over there, however is going to make most sense to you. And then the last thing I would do is clean this up a little bit. Distribute the 5 into here. 5 times m makes 5m. The 5 times 2 makes 10, plus the 1 makes 11. It's not much of an 11. That's a bit better. And then in the second set of parentheses, all you have to do is combine like terms here. The positive 2 minus 3 makes for a minus 1, so you've got m minus 1. This is your final answer. So that's the idea of substitution. It's using some kind of a let statement. You don't have to use the letter u if you don't want to. You could use x. I don't recommend using x because look at these other two problems over here. 13 and 14. They both involve the variable x. So you definitely wouldn't want to use x for those problems. Also, a final answer in terms of u like this is very unusual to have that as a final answer. In the world of math, your final answer typically isn't in terms of u. So if you're doing an online homework assignment and you go to type in your final answer and you're typing in the letter u, maybe that will be a quiet reminder to you that something's not right. I shouldn't be typing in u's, I should be typing x's. What's going on? Where did the x's go? Maybe that'll remind you that you've not done that one last little bit of work of replacing u with what you declared that it was equal to. In this case, m plus 2. All right. Number 13, you would use the same process of u substitution that we just used. And in number 14, it's kind of cute. I don't want to go all the way through it, but I would rewrite number 14 as maybe m squared minus n squared. That way you can see a little bit more clearly that it's a difference of squares, like a squared minus b squared. In fact, maybe using a and b is better. A squared minus b squared, because when you factor that, you get a minus b times a plus b, or a plus b times a minus b, whichever one you want. That's it. All you've got to do is plug your x plus 3 and your x plus 5 back in place of a and b, clean it up, and put a box around it. You'll have yourself a final answer. I hope that's helpful in giving you a head start on how to work with these 3 different factoring scenarios. The best way to get good at these is by doing more problems. So watch other videos, use the additional examples that are available in your online homework assignments, use the examples that are worked out for you in your ebook, perhaps. You don't have to tell anyone that you actually used your ebook. Just go in there and find some factoring problems that have the worked out solution process. Cover that solution process up. Try to do that problem on your own, and then slowly slide the paper down to reveal the textbook's solution process and compare it to your own so you can see if you're on the right track. All right, I'll let you get to work. Thanks so much. See you soon.